Growth and death is what equals health. So my equation for health is growth plus death equals health. Our bodies have to kill themselves correctly. Our cells have to kill themselves correctly for us to be healthy. Now, when we're in development, when we're growing, part of growing is also dying. So when our cells die correctly, it helps shape and mold our tissues and organs and our nervous system and our brain. So again, like a sculptor would add clay and subtract clay to get the final result, our bodies also add material and take material away. And the part of the body that takes material away through this cell death is called apoptosis. It's called programmed cell death. So that is one way that our bodies initiate this process of cell death, is when we're in development and we're shaping and molding our tissues and organs. It also helps remove the webbing between our fingers and toes, is the process apoptosis. Now, apoptosis or programmed cell death can also be initiated through DNA damage, viral infection, oxidative stress, the accumulation of reactive oxygen species, or ROS. Heat shock can also initiate cell death, as well as external signals can also initiate programmed cell death or apoptosis. Now, when a cell goes through apoptosis, it is a way for it to die and give all of its material to the neighboring cells in the area so they can use the amino acids and nucleic acids and even the organelles to their own benefit. If a cell dies incorrectly, it can actually cause an inflammatory response and a whole immune reaction in the area. So again, programmed cell death is the proper way for cells to die, and it is critical for our health. Now on the board here, I want to illustrate a small aspect of apoptosis and highlight specifically how we use iron and calcium in the process. Okay, so on the top of the board here, I have it labeled, the process labeled by number as we go forward. So at number 1, we have a FASL. Now FASL is a first apoptosis signal ligand. So that is the first signal in the process of apoptosis, and it is a signal that is connected to a neighboring cell. So up here would be another cell, and this chemical signal is actually attached to the neighboring cell. Now when that binds to the receptor, the FAS receptor, it causes a protein called FADD to turn these caspases on. Now these caspases, there's actually a family of caspases, and these are enzymes. Now these caspases are synthesized by the cell, but they are not active. They are called what's called a proenzyme. So these enzymes are sitting in the cell dormant. They have to be activated by a signal, and in this case, it's the protein FADD that binds to the receptor FAS, which causes caspase A to become active. Now again, it is synthesized in an inactive form, and it can be, when it becomes active, it breaks down our proteins non-discriminately. It just starts breaking down all the proteins in the environment without any intelligence. It just starts breaking down our own proteins. That's why it is inactive in the cell. Now, one thing that this caspase A does is it triggers the mitochondria to release cytochrome C. And this is where we have our iron. Cytochrome C requires iron for it to fold and function correctly. So cytochrome C has an iron molecule attached to it. Now this caspase 8 causes the mitochondria to release the cytochrome C, which has an iron molecule attached to it, and this eventually binds to the endoplasmic reticulum, which is another compartment inside the cell. And inside the endoplasmic reticulum, we have calcium ions. Now, when this cytochrome C binds to the IP3 receptor, that is inositol phosphate 3 receptor, which is a pseudovitamin. It is B8, which is a pseudovitamin. A pseudovitamin. When the cytochrome C binds to this IP3 receptor, it releases calcium into the cytoplasm, where it goes back and it binds to the mitochondria. And when this happens, the mitochondria becomes more permeable. And when it becomes more permeable, more cytochrome C proteins can leach out into the cytoplasm. Not only are the cytochrome C proteins leaching out into the cytoplasm from the mitochondria, other apoptosis chemical signals are also being released by the mitochondria. However, it's this cytochrome C that came from the mitochondria that turns on a caspase 9 enzyme. Again, this is dormant in the cell. It needs the cytochrome C to activate it. And again, once this becomes active, it starts breaking down our proteins. So this cell is actually shrinking because of this. It's getting smaller. Now, a cell that dies incorrectly actually swells and just bursts. But this cell, because it's going through the programmed cell death cycle of apoptosis, is actually shrinking. Now, this caspase 9 is breaking down proteins, but it also activates another enzyme called deoxyribonuclease. Now, deoxyribonuclease breaks down our DNA for us into nucleic acids, which allows cells in the environment to pick it up and use it. So that is basically just a small fraction of this apoptosis pathway. And I wanted to illustrate how we use iron and calcium in the process. Now, this is, again, apoptosis. And I just did a very basic search for other vitamins that are essential to this process. Vitamin D, K2, vitamin C, E, and A had all come up in multiple search criteria, as well as glutathione. So again, health is really growing and dying. It's not just growing. So if you want to be healthy, you have to be getting what you need for your cells to trigger this critical process in the body of programmed cell death or apoptosis. I will leave all my references in the description box.